Thank you, Karina, and thank you all for joining us today. And I'm gonna have to say, because I've been practicing for weeks, colloquy. Thank you. And like Karina said, this is really here to promote connections and to really talk about technology in a way for people to understand and talk about it in a good way. So again, I promise none of our panel will bring up the Terminator or Skynet throughout this presentation. As Karina said, there's 7 minutes, and I want to warn my panelists. She said she'll cut off a finger if I don't stick to that, so I'm going to. But let me tell you a little bit about Block Ventures. So my name's Bruce Beckloff. I'm the CEO and co-founder of Block Ventures. We're a permanent capital vehicle. So what does that mean? We sell shares in Block Ventures to use that money as working capital or investment capital. And we did that for some specific reasons, because where we invest is what we call the deep in the tech stack. And so just to describe this, if you guys didn't see my amazing podcast from Palo, I described some of this, but what we call a tech stack is every business, all the businesses that you work with will have a technology stack. Applications at the top, all the way going down to the hardware and things very deep in. And where Block likes to invest is deep in that tech stack. We really got off and going because I spent about 12 years at ARM, and surprisingly, I'm not going to point the person out, someone in this room didn't know who ARM was, and that's it. Anyway, and also my co-founder was from Vodafone, and so we all had operational backgrounds, and what we saw in the UK was an unbelievable technology ecosystem, unbelievable brains, but unfortunately not the commercialization skills or the capital to really get that going. And if you look at ARM's playbook, they were an amazing group of Cambridge engineers, and as soon as they got to a certain level, they went over to the States, got an American running around selling their stuff. No surprise, my accent. And in fact, we embed ourselves into the companies that we work with. I myself am also the CEO of a company called Yellow Dog, and Yellow Dog is very relevant for today. It's a company that gets very large applications, like a quantum computer application, and marries those up with computer resources. So for example, we did the 6th largest supercomputer in 50 or 33 minutes with our friends from Amazon. Some of them will be in the room to do a drug discovery that would have taken a year and took us only 7 hours to do. So this is the kind of stuff that we can see already going on with traditional compute resources today, and also the ones that we'll see in the future with when quantum and more AI come on. So I'm not going to talk about those technologies, so I'll leave 3 points with you. I have a theory of relativity, and all of us around here, and many of us older, younger, whatever, are all thinking that technology is accelerating. I personally think it's a pretty linear increase, but it's all relative to you. If you look at the printing press, at those moments, those people around would have thought it was going through the roof. Whether you look at, when, even fire or something like that. So for us, it's really amazing to see what's going on, and it feels scary. But actually, for our children, they'll be used to it. They'll understand it, and by the time they get to our age, they'll know how to implement it and look at it. So I think it's all relative to us. And that technology that they're going to learn, and we're learning today, they're tools. They're just simply tools. Deep tech is a tool. AI is a tool. And actually, some people find it a bit dangerous that my son now can write his entire 2,500-word Macbeth essay from ChatGPT. I'm not sure I'm so worried. I'm actually like the fact that he's now going to have to learn what Macbeth was about, or learn about what those subjects were about, not just regurgitate the facts that you can find on the web today. So I think those tools are going to change the way teaching happens, learning happens, everything happens. And I'm not sure that's such a scary place to be. And with that, the last thing that was out of my podcast, that I think of a technology stack as in Jenga. And if you all are familiar with it, gosh, if somebody didn't know what ARM was, I hope everyone knows what Jenga is. But technology is like that. It's a tech stack is a building blocks of a lot of other technologies. And so why do we have a permanent capital vehicle? It takes a very long time to get deep tech off the ground and integrated into systems. If you look at ARM, it was incubated inside of Acorn for 10 years. It then spun out for 10 years and IPO'd, and then it finally hit its first billion about 10 years later. It's now about 40 years old. So if it gives you the scale of what the things are. Now, that doesn't mean we're not seeing some things come on sooner. I mean, if you look at the things going on in AI, it's embraced more heavily. We've got enterprise-grade companies that are putting out AI like Microsoft and such. And so we may see a lot more adoption quicker. But nonetheless, it's going to take a long time, but it will change our lives as we know it. So that's the end of my talk. I'm going to hand over to Steve. What we're going to do is we're going to get into some specific use cases and then try to wrap it up at the end and try to get an idea of where things are at. So Steve, I think you were going to take us through the thoughts on communications.
Yeah, thanks, Bob. And going from one American to a Brit, you could tell from my East Putney accent. No, I'm just kidding. I've been here for 12 years. I'm going to talk about quantum security. And some of it may scare you, because it should be scary, but I also want to talk about how do we make it for good. So to start things off, I'm going to do a little experiment here. So I'd like everybody to take out your phones. Okay, everybody kind of pull out your phones. I kind of want to see everybody's phone. Unlock your phones. So if you got facial recognition, your thumb, can you please unlock your phones? Okay, everybody ready to go, yeah? So what I'd like you to do is pass your phone to the person on the right. Okay, only 1 minute, only 1 minute. Pass your phone to the person on the right. Now, the person who you get your phone, some people are really passing their phones. Actually, it's kind of surprising. For the other people that, go ahead and look through their phones, look through their photos, look through their documents. I mean, if you really want to snoop, you can do it for about 2 minutes. I'll give you some time to do that. I heard a lot of laughter. I see a lot of people feeling a bit uneasy, a bit vulnerable. How did that make you feel? So imagine that quantum computing has the capability to remove any encryption that exists in the world today. And that's the feeling that a lot of companies and people will get. Again, this is kind of, that's reality. It's a new technology, and it's not good or bad. Quantum isn't good or bad, it's what you do with it. So that's the reality of what you can do. I'm sure that the first people that discovered fire, there was a group saying, oh, stay away from that, you'll get burned. And others saying, oh, that's going to be a great technology, we can leverage that and scale it up. And this is the same thing with quantum. So depending on how you look at it, you can look at it as a force for good, or kind of be fearful as a force for bad. But we're going to talk about how do we use it as a force for good. There was a professor from MIT. When I did my quantum studies, I learned from him, and his name's Peter Shor. So Peter Shor wrote an algorithm called Shor's algorithm. His algorithm will break any encryption with a strong enough quantum computer. And so that's kind of where we want to look at how do we protect. And the good news is there are technologies out there that are being looked at, that are being implemented today to do that protection. And I know some of the skeptics in the room will say, well, Steve, even the best experts say it's only a 3% chance that a quantum computer in the next 5 years will be able to break the encryption that we all have and that we all use. And 3%, you might think, that's not too bad. Does anybody remember in 2020 what happened in 2020? So I live in Wimbledon, and the Wimbledon, the actual tennis, they actually paid insurance for pandemic insurance. And when you looked at when they paid for it, there was only a 1.5% chance there was going to be a world pandemic. And everybody thought, oh, they're silly, 1.5, whatever. But here are kind of the silly ones where everybody that didn't have it. That's 1.5%. This is a 3% probability that in the next 5 years, there'll be a strong enough computer to be able to break that encryption. So that's really important. I know there's a lot of people in here that work with the US government. So the US government, so the White House actually put out an executive order saying that anybody that wants to sell or work with the government will be required to be PQC compliant. Yes, I'm gonna, PQC is post-quantum cryptography. That's what the mathematicians love. The quantum physicists love QKD, quantum key distribution. I won't get into the technical stuff. But so these are things that they're looking at. And so the government is saying, look, if you want to work with us, or if any of your suppliers want to work with us, you have to be post-quantum cryptography compliant by a certain date. That's the first country that's doing it. There's other countries that are going to follow suit, and I can see that there's going to be a lot of regulation around this. So my suggestion is to get ahead of it, educate yourself, really understand, what it is, what it isn't, and how do you protect yourself. It sounds scary, but it isn't. It's about really understanding kind of what solutions are out there and how you're going to be able to do it. There's a lot of companies like Apple, if you guys have your Apple, or if you guys use Zoom, they've already implemented their PQC algorithms, post-quantum cryptography, sorry, Karina. How many fingers did I lose already? Because
You've got 2 left.
Yeah, I got
two fingers left.
Okay. And so you got Apple, you got Zoom, and a lot of these companies that have already implemented. Just recently, the NIST, the National Institute of Science and Technology, just released their official 3 algorithms for companies to start using to protect their environment. And so if there's anything I'm going to leave you with today is understand PQC, understand QKD, which I've already said what they were, and learn about crypto agility. One last plug, I also have a podcast. And so next week, I'm going to be doing a free LinkedIn Live for anybody that really wants to understand this. You could just join, go to my LinkedIn, you can understand this. But I'm telling you, this area is getting hot, and I think that there's a lot of really great opportunity. But look at it as a positive thing. Don't get nervous. Get in there and educate yourself. Thank you.
So spot the Americans. So far, you've had 2 people talk, and we both promoted our podcast. Well done, us. So, Julie, we're going to move over to you and talk, sort of government perspective, also some of the thoughts around where these things are being implemented around net zero.
Okay, thank you. So I don't have my own podcast. I have got 10 fingers, and I'd quite like to hang on to them. If that's okay, Karina.
All right, the clock started.
All right. Okay, so I'm Julia Sutcliffe. I'm the Chief Scientific Advisor in the Department for Business and Trade. I've been there for about 18 months. It's been a super exciting journey, underpinned as it has been by great advocacy and appetite in government for science and technology. So that's been really interesting, and that continues with the new government. Before I took this role, I was a chief technologist at BAE Systems and also sat on the Science and Technology Board for NATO. And my day job was really about pushing AI technology into every aspect of what we were doing, from design, development, support, training, and also looking at quantum technologies, particularly sensing, timing, navigation, where that could give us differentiated capability. I mention that just because I want to sort of articulate how vested big business and corporates are in these technologies. This isn't just something in the SME community. Sorry, that's one acronym, but is that okay? In the small business community, large corporates are really interested in this because of its transformational potential. If I go into the very distant past, I did a PhD in quantum technology, and my first ever job was to look at the state of the art of AI for its application in defense and aerospace. And I mention that simply to reference the kind of time frame of development of some of these technologies. Without giving too much away, obviously that was a couple of decades ago. But that sort of identifies the richness of the science and technology R&D base that is required to get to where we are today, which is a fantastic baseline of science and technology, ready now for us to supercharge that into innovation and into new products and services. Okay, so the new government has articulated 5 key missions around clean energy, NHS, growth, opportunity for all, and safer streets. And AI and quantum can play a significant role in that. At DBT, we support businesses to grow. So we want the businesses that are currently forging ahead in these technology areas to grow. We want more to come along, but we also want more of the adoption and diffusion of these technologies through the economy, so we get increased productivity and opportunities in existing companies. So in the city, these technologies could mean utilizing quantum to increase security and speed of transactions, We could be utilizing AI to support the back-end coding and interfacing. But if we look at the sort of key challenges around health and climate, then as we've already heard, lots and lots of opportunities are present. So if we think about the NHS, we have a huge database now from the COVID-19 pandemic already mentioned. We're looking at utilizing that through the NHS AI laboratory so that we can improve treatment. AI is being deployed at the Addenbrooke's Hospital for improving cancer treatment, really increasing the rate at which patients can be treated. And also looking at Biomedical Sensing Hub at UCL and Cambridge, we're looking at treatment of diseases such as Alzheimer's. In terms of renewable energy, AI is fundamental to helping us understand how we optimize across the grid, how we bring renewables into the grid, how we do battery storage most effectively. And quantum technologies can help us through rapidly cycling through opportunities to create new materials to support those battery technologies that we're going to need for the storage we need, given the massive demands we're all placing on the grid. So lots and lots of opportunity there. In terms of some structure, what do we do in DBT? We help businesses grow. So we try to connect the ecosystem. We try to connect businesses with investors. So we do trade missions. We also run the global talent network that supports bringing talent into the UK. And of course, we work with free trade agreements. So we have the first innovation chapter between UK and Australia. So we bring a technology focus into those agreements. Clearly, as we know, taking technology and transitioning that into tradable outcomes is going to require an all-of-government approach. We need tech, we need skills, we need infrastructure, we need finance, we need access to markets, we need appetite, we need advocacy. So we work very closely across government on some key programs, particularly on AI and quantum. So you'll know all about the Quantum Hubs program, the £1 billion of investment that's gone into quantum over the last decade, which has been an excellent program to generate some real maturity, and we now carry that on through the hubs. There are multiple activities on AI. You will have all been aware of the AI Safety Summit and the work last year there. Now we move into AI opportunities. So there's an enormous amount of work going on. And in terms of investment, working with the British Business Bank, you'll be aware of the Breakthrough Fund for Innovators, and also working with other institutional investors to try and crowd more investment into this space. It's all to play for. I'd like to give a huge shout out to yourselves, whether you are a developer, a technologist, or an investor in the audience today. Bringing you together is fundamental to our success, and I want to thank you for everything that you've done to date. I think it's all for us to play for. It's a really exciting time. Thank you.
Thank you. I have to say, it's the best self-regulated panel I've ever seen. I haven't even got to use my watch once. But we'll move over to the investors, and so that's always a dangerous way, and talk a little bit about life sciences. So Ola, maybe you could take us through where you guys see things going in AI and pharma and how that's changing things.
Yeah, fantastic. Hi, it's great to be here, and I want to thank Karina for giving me the invite. My name is Ella, and I'm an investor in life sciences, or what we call tech bio, at a growth fund based here in London. And we're always asking ourselves the question of what's next in life sciences? How do we crack the life science problem? And the biggest problem that we have today is being able to design safer drugs quickly and get it out to patients. And this is a massive problem for us in the pharmaceutical industry. It currently costs around $1 billion to get a drug to market. And even then, only 1 in 10 drugs actually succeed. And it takes us 10 years to get there. So the first question we asked is, how can we improve this? And the way that we have improved it, and I'm glad this is being brought up, is with AI. AI has helped us create a lot of operational efficiencies that have compressed these timelines and have helped us improve design safer drugs. And now at my fund, at Kinnevik, we're asking the next question, which is AI is here. It's improving the way that we're designing drugs. What's next? How can we improve this even more? And we have two problems that we're trying to address. The one of trying to design better drugs, and then the first question which begets this next. And that one is, how can we understand ourselves truly? As humans, we have multiple dimensions. We're dealing with different chemical reactions that all occur simultaneously. It's a question that AI cannot solve and cannot help. And that's where we turn and we look towards quantum. Quantum and the use cases that we're most excited about is helping us to understand ourselves and our chemical and biological processes better. And if we can start from that foundation, simulating a body and designing what we're calling a digital twin, we can then, from that foundation, design better drugs faster and more safer. So the case studies that we're most excited about in quantum that we're looking to invest in are companies like Quantify, and Hans will speak about it soon. They're trying to simulate all of these complicated chemical processes that happen in the body. And by simulating them, we can start to understand exactly what goes wrong. And when we know what goes wrong, we can design better drugs. And that's the first use case that we're very excited about in quantum and quantum for good. The second use case is a multidisciplinary one. It's one that asks, how can we design or even come up with better materials? So far, when we're designing drugs, they have a load of different side effects that are unsavory or unoptimized. And we're asking the question of, how can quantum help us discover, repurpose, and optimize better materials for designing safer drugs? So this is a use case that we're very excited about. My friends at Kinnevik, who also invest in climate tech, are also extremely excited about quantum applications for novel materials and fuel sources. And for us, we think this is the next frontier beyond AI and the AI revolution. It's the quantum one. It's the one that allows us to explore our bodies in multiple different dimensions and to design better drugs that are suited to our individual needs. So I think that's what I think of when I think of AI for good when it comes to quantum.
Thank you. Hans, how about you? Well, another investor, but now more in the sort of wetter life sciences.
We're not investors. We actually do stuff.
The briefing was wrong.
Ouch, Hans.
No, and
Have to talk about this later.
thank you, Ala, for the intro as well. So what we do at Quantify is fundamentally two things. All of it is software. So we work with computers to get other computers to work. We develop quantum software, which uses quantum computers, it's a different kind of computer, as I'm sure you're aware of. And fundamentally, how do you use that for useful things is still an open question. We're very bullish about the fact that the original use case for the quantum computer was to emulate nature. Nature is fantastically, but also ridiculously complicated. Quantum mechanics is mind-blowing, and it also doesn't fit into our normal computers, which makes it really hard to predict how chemicals react in the body, for instance. Quantum computers are uniquely suited to replicate that, the physics, basically. It's the same physics. And so we're very excited about applying quantum computing to that, and there's a lot of engineering going on the quantum side in order to leverage that power. And trying all the different computers, but it's not enough. So we spent the last 40 years trying to simulate nature on the normal computers, getting rid of all the quantum pieces because it was too complicated. And now we sort of have to drag them back into sort of our basic way of also calculating things on the normal computers, given that we now have this power. So there's an enormous amount of re-engineering and rethinking going on, also on how we actually compute things on what we call classical computers or normal computers, in order to make space for the quantum computer and leverage that power. So it's sort of it's going to be a partnership between normal computers and quantum computers for as far as we can see, just as we today use normal computers with graphics cards for different things to do useful things. So we work at that intersection. What we focus on is drugs. And simulating the interactions between drugs and the body, as Ella also mentioned. And that is hugely exciting because if you can make a difference here, I think there's hardly any more interesting chemical reactions than the ones that could lead to better treatments and better outcomes for patients. So we're laser focused on that, working on both the quantum piece and the classical piece. And just to say a little bit about how AI and quantum then play together in this magical future that we're very close to, and much closer than I think many of us realize. So AI is a pattern recognition machine. AI is trained on huge amounts of data, and it will find patterns that no human would ever be able to. But it doesn't work without data. And it's really bad at thinking outside of the box, quite literally. So whatever you train the AI model on, it's very informed on what it's trained on, and everything outside of that is poorly understood, which is an issue in life science because we want to attack diseases we don't understand. We want to find cures for things we haven't studied for 40 years. There's plenty of places where AI has and is making fantastic progress today, but it's the thing we have already understood and studied and created data in labs all over the world for the past decades. So what do we do with the new things that we don't understand quite as well? We need some machine to generate the data. And you can use robots, which we do today, that screen hundreds of thousands of small Petri dishes automatically and then generate a lot of data, but it's expensive and it's slow and the quality is not perfect. Or we could imagine a future where you have a physics machine that accurately calculates what interactions between the different molecules actually take place in the body. And there are so many different molecules that even if we have very large quantum computers, even decades from now, they won't be able to calculate everything. So we'll end up in a place where you use the quantum machine to generate the data, and you use the AI model to figure out the patterns that we can't see as humans. Then AI has a second problem, which is it doesn't understand physics. It's a pattern recognition machine, and if you played around with these, it's called diffusion models, the ones that generate pictures, you'll see they don't understand letters. Like they have the concept of letters, they can do Lego boxes, but it's not quite letters. And it's the same models we use for molecules. So it looks like molecules, and sometimes it is molecules, but sometimes it's not. And so how do we teach the AI machine what is a molecule and what is not? Again, you need the physics machine that says this is good, this is bad, and you can do something that's called reinforcement learning and train the model to actually become better at spotting what can actually work in nature. Because we want to find fantastic molecules, but we want to find the ones that we can actually make. Otherwise, it doesn't really make a difference. So that's how we see the interplay between quantum and AI, and I think this is the thing I am most excited about with a quantum computer, because I think it's somewhere we can get quite quickly, because simulating chemistry on quantum is the first thing we believe will become useful in the future.
Thank you. And I know I'm going to get this one right. We'll round it out with Aham, who's chief scientist at ENQCC. Where are things at, and how are we going to get these technologies out of the lab and into the mainstream?
Thank you. Hello, everyone. So as mentioned, I'm NQCC Chief Scientist. I'm also in collaboration with NQCC leading a 60-plus quantum researcher at the University of Edinburgh, every day trying to publish paper, writing code, trying to figure out what is quantum useful for. So your next City of London summit might be up north, who knows? The only reason I'm mentioning this, I want to say that I'm going to talk about low TRL. I'm going to talk about all those golden things that we dig out to share with you guys to make money out of it. So bear with me. I'm going to go a little bit to the base. So we already heard about lots of exciting that AI can do and quantum can do. We all want it. We want to have it, to work with it. But I know, and this is about all being good, so allow me to also mention a few challenges. In order to really achieve everything that we're dreaming to achieve, drug discovery, net zero, quantum material science, etc., we have to address three key issues, both for AI and both for quantum: scalability, integrity, and privacy. You know, just to bring those issues to make sure we are all on the same page. Nobody's going to share their data readily with Amazon in order to discover a new drug, you know, without going through the very complicated IP collaboration, etc., etc. Nobody wants to run on this magical machine that we don't know what it is, something that we don't even know if it's really done it or not, because it's noisy, because it's fault tolerant, because it gets just a bunch of numbers. So how do we know it's doing what it's supposed to do? And nobody right now knows how to scale it up. We cannot scale up AI any more. You know, how many more GPU we want to do? The planet will collapse after all. And even quantum needs to collapse. So we have to deal with all those issues and all those issues of privacy, integrity, and scalability. And the good news is that they can all go hand in hand. AI can help quantum to scale up. There is many examples for calibration of QB, to looking at the noise model, the scalability, etc., forever I can talk about, but people in the room are familiar. And quantum can also answer those questions. And particularly, I'm going to focus on the privacy, because I think we have mentioned it, but not enough. Really, we have an issue right now regarding privacy of AI. We all want to do it. You're happy about your son reading Macbeth, but you might not be happy to see what information about your son is going to be leaked when they're using ChatGPT. And now scale it up at the really industry level. If you really want to use the AI for a toolkit, we need to figure out how to dig out who has the data, who has the machine, who has the solution, how do they going to integrate into each other. So, and that's where the magic is, at least academically we have proven, wait for you guys to spin it out. But the point is, quantum communication and quantum by the nature can actually solve that problem. So quantum computer like Shor's is going to break the hell and we don't like it and we want to come up with a solution. But actually quantum communication, the same way that solves some of our normal communication security, solves the privacy of AI. We have looked at the differential privacy, privacy preserving. So these are all the issues that we have a solution. In particular, we have looked at back to the life science, which is the topic of the day, regarding, for example, in genomic. Genomic is another direction that we love to use, whether it's large language model to be trained in order to discover the new disease, or use quantum. And why use quantum? Because it allows us to go to the higher level order of the evolution. So we can capture probably correlation among the data that we cannot capture with AI, as we have got it, but it's exactly the moment that you cannot do whatever you want with your data. So you need to create, in all of our papers and publication, we're using artificial synthetic data to do so, but in reality, if you want to make them as a technology, a toolkit that everybody put the bits and pieces together, we have to solve the issue of privacy, integrity, scalability, and we can do that using magic of quantum. So I'll stop there.
Well, very good. It's a very well-trained panel, Karina. Well done. So we've got some time now for some Q&A, and I'll try not to answer every question. Is there a mic to be around, or? Ooh, there's a clock that's ticking down. Do I need to touch screen? Okay.
There's the mics. Hero.
I imagine most people in here have very loud voices anyway. You all look very successful out there.
Thank you. John Harrison, I'm Chief Scientific Officer at Scottish Brain Sciences, and that's made it worth coming already, so thank you for that. I love the idea we have a technology that we can bring to large data sets. My concern would be the quality of the data that's going to get in them. You spoke about drug failure rate. In my area of Alzheimer's disease, we have a 99% drug failure rate. Although we probably had drugs that worked, we just didn't have the wit to find it. And unfortunately, pharmaceutical companies do an abysmal job of running clinical drug trials. So I wondered if there were an opportunity for perhaps Professor Sutcliffe and colleagues to get together and just set out what a good data set looks like and what it should contain.
I can give it a go. It's impossible. So it really goes back to that gritty details that you're saying it. So not only the quality of data that's coming there, and also digging those data into the machine is another second level of the problem that you're saying. So I would say usually answer, at least in the AI community, people can add it, is that you doing a training machine for that particular set of data. So over and over, we have learned that there is not universal solution fit all. So it's not the case that, we just train one large language model and then we just dig into the parameter. So the answer is that when such a primitive is really required, you really need to put the data scientist, the designer of the neural network, the designer of your quantum device, the designer of everything together, so they train it for that specific data. That's the best way that comes to my mind. So.
Yeah, I agree. I might even go further to say that it's a bit more fundamental than that. In science, we have a reproducibility issue where a lot of the published research is actually inaccurate, and that's to do with a lot of inconsistencies in labs as well. As a genetic researcher by background, we've had this problem even in the top publications. So we definitely don't have the answer today, and it does seem to be a potential solution in just scaling it. More data, more access to initiatives that are working with public healthcare systems that give us that feedback loop. So how are patients responding to drugs? What are people's long-term disease outcomes looking like? I think over time we can improve it, but if there is a solution at the tech level, then I'm really curious to hear about it as well.
Can I just jump and say, in order to enable your fantastic suggestion of public data, we need to address the question of privacy, because otherwise people would not share those data. So I think they go hands in hand.
For sure.
Hans, did you want to say something?
Yes, because and allow me to go off on a slight tangent, but this is actually a place where I'm very excited about quantum and more than AI, because one of the hard challenges about Alzheimer's is getting drugs into the brain. And the brain is a physical barrier, it's a different membrane than other parts of the body. And we don't have very good tools to get an understanding of how drugs penetrate at the moment. So what we do is we put mice cells in a petri dish, we sort of treat them to behave like a membrane, and then we try to put drugs on one side and see what comes out on the other. Now, obviously that's wrong, because we're not mice, we're humans. And we're different, right? So there's different races and ages, and your brain membrane is different depending on your genetics. So, but it's the best we can do today. How do we do it better? If you can't get brain cells out of a living human, they stop being living. So what do? I think the best bet for understanding blood-brain barrier penetration, and sorry, that was a little technical, is a simulation on a computer. And we are very actively working, so that I'm plugging myself and our company, we're very actively working on simulating blood-brain barrier penetration. Because if you can crack that, it's realistically the only way we'll be ever able to take in all the different options of humans out there. And we're very far from personalized medicines, but maybe we could just have men and women, and that would be a step forward from where we are today. And that simulation will happen on a computer powered by quantum, I think, within the next decade. And that will be a huge leap forward for our ability to develop drugs that target any central nervous system's diseases, and Alzheimer's in particular.
So thank you, Hans. I'm going to move over to the screen. Now I could do this one, so I'm going to let one of the panelists. Could somebody, please, in the simplest terms, explain the difference between quantum and traditional computing? Hans, you've already gone. You're going to have to let somebody else go.
Can I try?
Oh, you can go.
A normal computer is binary. You've all seen the matrix with the zeros and ones. So it operates, and in the olden days it was a transistor that could flip very physically if it was a 0 or a 1. And you can do a lot of fancy math with a computer, and all of you have one in your hand or in your pocket right now. It's an iPhone or whatever. That's a computer that works on ones and zeros. Very powerful machine. Nature is different. Nature operates with quantum physics, which has all kinds of strange behaviors that makes no sense to us, which is why quantum physics is sort of maddening. All the experiences we have from our daily lives, they don't translate into quantum physics. So nature, when it gets small, behaves differently. Things are not in one place at any given time. There are multiple places. Things like particles don't have one velocity. They have many different ones. And so if you have two things, like two balls rolling towards each other, like a set of billiards, you can easily imagine you have a picture in your mind of how two billiard balls would collide. You've seen it many times. That's not what would happen with two quantum particles. You see a cloud of particles that would come towards each other, and you'd see a pattern emerge from that cloud. There's so many different variables going on for the quantum world that it doesn't fit in our normal computers. And the only way we can get nature to fit in a computer is to have a computer that behaves the same way. So we don't use bits, we use quantum bits, which can have the same behavior. So they can be in multiple states at the same time, which doesn't make any sense. And you can operate on them, you can do math with these bits. And then the whole question is, how do we get power out of that? How do we make it useful? Well, Shor came up with an algorithm, so a formulation of how can we actually find large primes, and that's how we break cryptography.
Steve, do you want to give it a go as well?
Just very simple. Think about two mazes, right? So you got your classical computer on one side and your quantum computer on the other side. A classical computer is serial, so it'll try each part of the maze and then come back to the start and try again. A quantum computer goes through every single variation at once, goes to the perfect route, and it gets it right from the beginning. So that's the power of quantum computing, that can have that exponential value, because it goes straight through every possibility, where a classical computer would take millions of years to actually be able to do that. And because the world around you is quantum mechanical, a classical computer could never simulate what we have around us. So for us to solve some of these real world problems, you need a quantum computer. I don't know if that makes it simple.
We're going to go to the next question because I think we're going to have to shorten that elevator pitch. Over here.
Hi, thank you for that. My name is Zara. I'm an AI and frontier technology expert, and I serve on several boards. I have a bigger picture question. As you know, the EU AI Act has lots of challenges due to its risk-based approach. And UK no longer being a member state, that causes other issues for us that I wouldn't go into detail. What does the panel propose that the UK could do in terms of implementing its own AI regulation that is balanced, fair, it also fosters innovation and serves the greater public good and mitigates AI issues such as hallucinations, inherent gender bias, ethnicity bias, privacy, which is the biggest issue. I sit on the ICO's Technology Advisory Panel. So what would you suggest? And what could we do in terms of bringing all the key stakeholders together, the private sector, the public sector, and the third sector, for the UK to actually have its own AI regulation?
The government lady.
Damn.
You weren't picking up your mic. I'm going, Julia, come on.
Okay, that's a great question and a really super complex topic. So one of the key parts of answering that is to think about the application space. So if I think back to when I was in the aerospace defense sector, we would bring in technologies, but they're always within a context. They're bounded within a context and get integrated into a system. And then there is analysis on the system itself, depending on what you're trying to use it for, that allows you to come up with what we would call a safety case, for example. So that doesn't mean that you are regulating the technology itself or the algorithm. It's what you're using it for, in what context, to do what. So I think that means that we need to be able to bring the multiple different regulators, whether they be in healthcare, whether they be in aerospace, whatever sector, to understand what are the use cases for AI in those sectors, and how do we bring an approach where everybody is educated? As you sort of said, there are multiple actors going to be involved here. So how do we bring that convergence so that we can come up with a useful set of rules dependent on the application and the sector? And I think the government has done is doing lots of things in terms of sandboxes, so being able to experiment within a regulatory envelope to bring new technologies forward. It's also set up the Regulatory Innovation Office just recently, so that we're sort of very mindful of wanting to embrace innovation, but also having some boundaries where we obviously need to keep the public safe. So there's a balance in all of that, and it's a sort of a specialist topic, really, dependent on the use case and the area. But it's a great question. I haven't got a single pithy answer for you.
Maybe I add something. I don't know about AI. It might be even late, so given the status of the affair. But at least in quantum, we are doing it. And UK Quantum and NQCC, together with the colleague from MPL, they are already leading the same question that is going to be valid very soon for quantum. And exactly the same approach that you were mentioning. Back to the application, back to the case. And maybe even, at least this is a message for us, within the quantum effort with trying to answer all this issue that you're saying, at least maybe AI can come to it when it's come in the intersection with quantum. So we are learning from the so-called failure in the case of AI to make sure at least we don't do the same mistake in the case of quantum.
I'm just going to add from an investor point of view. I mean, we've got two good bookends to look at. We've got the US, it's pretty open on AI, and you've got Europe that's really come down with some very difficult regulatory environments. I can genuinely say that startups are mobile and they don't need to be any one place. That's one thing that usually they may be in the university they come from, but once they spin out, they have very little money. They're going to go where they're going to be able to get that startup up and going. And so I'm not saying I have an answer, but the challenge for the UK has the opportunity to be in the middle of this, where the EU is too much and the US is too little, and we could be right in the middle where we just, it's sort of the three bears, we get it just right. I don't know if that can happen or any answer to do it, but we definitely need to make an environment here where the startups, yes, we're trying to regulate everybody at once, but there's going to need to be some kind of environment where the innovation is allowed to foster. Otherwise, we will completely get left behind in the US. I mean, we're already behind, but we've got to figure out that environment that actually creates the innovation. Otherwise, we're really in difficult times. So,
could I just add one other thing, that we've also got the AI Safety Institute that's been set up, so that will be a real point of focus for addressing the questions that you've asked there, because, yeah, it's a challenging topic.
next question. Mr. Turner.
Thanks, Bruce. Air Marshal Andrew Turner from Space Foresight. I want to applaud Karina's drive for speaking in plain English, because I think this is a real barrier to the progress of quantum in the country. And it speaks a little bit to what Julia you just said around use cases. I feel that there's a barrier between the development of the science and the investment in those products and the users ultimately. I think there's a real difficulty with the mythology of the language, the impenetrability of some of the science, which frankly very few people properly understand, and the ultimate deployment of the science in society, defense, biosciences, infra, fintech, wherever else that might be. Can the panel suggest how we might better penetrate the country with the science?
Spark program and QCC.
And?
I think education is big, right, in understanding it. And I'm sorry, Karina, I've got to plug in another thing I'm doing. I'm teaching quantum strategy at MIT. We're launching a course, and it is for business executives and for government leaders. When I got into quantum, I used to work at a bank, and back when Nature published its magazine in 2019, Quantum Supremacy, it scared the hell out of the banks. And they wanted, I used to be the head of innovation there, they wanted me to update the bank, and I had a moment where actually I had to go out and learn about it, and I did it the hard way. And I went and I had to learn the maths, I had to learn all of that stuff, and I saw an opportunity in the market where we could teach for executives, right? We all have phones. We don't know how the phones work. We don't know what all the technology inside, but we know how to utilize it. And I think quantum will have that same point where we don't need to all understand. You don't all need to be quantum physicists, but you play your part in how you engage in that ecosystem and work. So just a plug, we're releasing a course for corporate executives January 1, and that coincides with the International Year of Quantum. If you don't know, next year, the UN Assembly made 2025 the International Year of Quantum. So there's going to be a lot more education, a lot more work going on in this space.
Steve, I might have to come down and high-five you for another plug. I mean, I'm going to just, Julie, do you want to take?
I was just going to add to what Steve said and said, yeah, the answer absolutely is education, but it's not a general level of education. So there are some interesting programs to actually bring investors up to speed with what some of the technology looks like. So I think the Kaufman program and the Newton Venture Fund programs that are trying to sort of do that partnership between investors, encouraging PhDs to go into sort of the investment community, but also partnering with investors so that you can understand risk and then take managed risk, so that we sort of try to bridge that gap between sort of large-scale capital investment and some of the emerging technology businesses. But it's a big challenge. It's a great question.
Can I also add, it's not just a matter of investor. And in fact, the reality is that even high-tech end user, take your NHS, as a potential end user, all the way to the science, the gap that you mentioned, it still exists. And I emphasize it almost in every single panel that I go in. And we have done everything we can do. If you see by we, I mean the academic community and even the startup community, the quantum startup community. It's really the very, very crucial moment to reach out precisely what you're saying. And it can start not necessarily from investor, but from the end user. It's one thing that, somebody read the latest result and trying to figure out if it's now relevant or not. But the reality is that we can really achieve the quantum advantage for a specific use case if we start to have a common language. I love to create that common language, and without that, we are not getting there. So I mentioned a Spark program because it's really is one of the things that we are involved with. Spark program is part of National Quantum Computing Center program to really bringing end user which are high approved. You know, they already know their problem very well, better than we do, and trying to match-make it with the industry, startup, and academic. So we're creating that high-level education that you're mentioning, and then hopefully then we can go to the investors to now take it forward. But it's a very crucial moment, so I'm happy you raised that question, because otherwise the death valley will come to all of us.
So just because I get to handle the mic, I'm going to take a contrarian view. I don't think you guys should really worry too much about knowing all of that. I mean, how many people in here know what a GPU is? That's because NVIDIA is one of the most expensive companies in the world, and you've learned what it does. And if you really look into it, why it does what it does, powers AI, those sorts of things, you don't know the detail behind. It's a bunch of units that go and does really good parallel math. I mean, that's not the important bit. You guys know that GPUs are important to AI, and that means they're important things to know about. So I think there's a difficulty. There's going to always, I mean, look, we couldn't even explain what a difference between a traditional computer and a quantum computer is in less than 200 words. It's kind of back to my Macbeth comment. You know, learn why it's important. What's important about quantum? You get all the answers at once. It's going to be really difficult to keep security tight. These kinds of challenges are ahead. Then figure out how that affects your business, and then get one of these guys to come in and figure out what the actual detail is behind that technology, because I think at that level is the language you want. Why is it important?
Hello. I just want to reiterate what that gentleman just said, and I hear what you've just said too. But I think the issue is if we're working with investors and we're asking people to allocate capital, we really need to understand what the risks are and, you know, what are the short-term use cases, what are the medium-term, what are the longer-term. Because unless, it's not just a question of understanding the technology, and I think we will all get there to the extent that you've just described. Our issue is, how do we explain to people what is going to happen in 5 years, 10 years? Where might they lose money? What is breakthrough research? What is, you know, real practical use cases? And we just don't have any kind of framework for that.
Collaboration. I mean, I insist, because I disagree that you don't need to know what is quantum, because quantum is a horizontal. It's not like quantum is going to solve everything. Quantum for sensing is very different than quantum for metrology, for security, for space sector, for computing, for biology, for simulation. So in fact, because quantum is very different than GPU that is just fast and accelerating AI, is actually going to change the way we think. I think we need to do a bit of all of us need to do homework. I need to do my homework to understand what is the use case, what is the benefit of the market, etc. And I believe the only way we can progress this by collaboration. Still, the sector is not so competitive that people is not really figure out the magic wand that, you know, I'm going to take it and not share it with everybody. So right now is a great moment, back to the case of the UK, with the Quantum Hub, with the ecosystem, with the startup, with the NQCC, with NPL, with the Hartree. We have all the elements. So my message is collaborate. Don't do quantum at home. You know, it's dangerous. You have to do it together.
Maybe I'd add really quickly is that you don't need to pitch it to all kinds of investors. You're right, if you can't tell where quantum's going to be in 10 years' time, it's a very, you know, developing sector. A lot of generalist investors don't have that risk appetite. But there are investors like Dan and others who have patient capital bases, who invest in these deep tech companies. And that's a better use of your time and your efforts to educate them and get them on board. And I don't think that type of investor would look to you to give them concrete answers and quantify risk, because they would be willing to take that risk on.
Okay, that's very helpful. Thank you.
Oh, yes.
Hi. Oh, hello. Tony Reeves from Deloitte. We've seen governments restrict and block access to things like end-to-end encryption. Do you think governments need to do the same for stuff like quantum encryption?
They do. They have said the similar things. To some extent, that's even the case for the quantum communication. That's why we have trusted nodes. So it is part of the same pack. And in fact, back to the case of when you're looking at the issue of how the quantum provides security, is another layer. You don't need to necessarily know that it's quantum communication or the quantum device or private communication using LWA or classical solutions. So any condition that exists regarding security, it's valid and is already implementing on the case of quantum communication, and we have solution for it.
Yeah, and there's export controls today. And so companies can export their technology, their know-how. Even in one of my companies I do consulting, I'm restricted of flying to certain countries and talk and train in these, even at the university, I'm not allowed to train certain countries or residents in this technology. So those controls exist today. I think they're going to get even tighter.
So just on the investment front as well, before we take on money in anything, it's National Security Investment Act. You know, we have to go ask the government's okay to take on money. We have to ask the okay if we're going to sell it. We're going to have to ask the okay. And the thing that scares me as an investor is, because clearly I want to make as much money as possible, you know, is any kind of restrictions that goes on for free trade to retain secrets through regulatory and government. Now, I have no issue. I don't want any of our companies to be selling to a bad actor, but I would rather that come through, you know, not through regulation and that necessarily, but working with the government to make sure I know where it can and can't be done. But there's a definite, just to give you all comfort, the government is definitely looking at all technologies that may be of national security, everything. So it's, whether it's quantum, security, anything out there, antenna technology, anything out there, it's being looked at. So either that could be comforting to you or not comforting because there's an overlayer of regulation, but it is out there. We've got 3 minutes and 35 seconds left. Oh, that killed it. That's brilliant. All right. Well, look, thank you to all the panelists and for joining us here today. Thank you for Karina for putting it together and allowing me to pontificate for so long. And again, enjoy the rest of the day. I've been here the last few years. It is good.